All right, today we are tackling one of the biggest, the biggest challenges in modern software. How in the world do you build a database that can handle millions of users all across the globe without just collapsing? We're going to dive deep into the architecture of distributed databases. You know, the hidden bedrock behind pretty much every app you use every single day.
So picture this. Your app just went viral. It's the dream, right? But oh no, your single trusty database is literally glowing red hot. It just cannot keep up. Every new user, every single click is just more fuel on the fire. And look, this isn't some made-up scenario. This is the moment of truth for so many companies, and it perfectly sets up the huge problem we're here to solve today.
You see, the second you move past just one single machine, you've just walked into a whole new world of pain. Seriously, your data is now scattered all over the place. Any one of those machines, it could fail at any second. And the network that's supposed to connect them all, let's be real, it's just not reliable. But through all of that chaos, your users, they still expect everything to be lightning fast and 100% correct. That right there, that's the core challenge. Okay, so how do we even begin to solve this? Well, first things first, we have to accept a fundamental law of distributed systems. You just can't have it all. It's impossible. Engineering is always about trade-offs, and believe me, nowhere is that more true than right here. And that brings us to the legendary CAP Theorem. This is such a crucial way to think about this stuff. Basically, it says that any distributed database can only pick two of these three guarantees at any given time. So, what are they? First, you've got consistency. That just means everyone, everywhere, sees the exact same up-to-the-second data. Then there's availability. This means your app never shows an error page, it always gives a response. And finally, partition tolerance. This is a big one. It means your system keeps running even if the network connection between, say, your US and European data centers completely dies. Now here's the kicker, the really interesting part. That last one, partition tolerance, it's not really a choice. Networks fail, connections break, it's just a fact of life, so you have to design for it. That means the real gut-wrenching decision for any architect is always between consistency and availability. So, what's it going to be? Do you want your system to be always correct or always on? All right. So with that trade-off in mind, where do we even start building? Well, the first hurdle we've got to clear is just raw scale. That one little database just isn't going to cut it anymore. The answer? It's classic divide and conquer. Let's talk about how we split this data up. Yeah, this whole process is called sharding. Think of it like slicing up a giant pie. And there are a few popular ways to do it. You've got range-based, which is super simple, but you risk creating hotspots, where one server gets slammed with all the traffic. Then there's hash-based, which is great for spreading the load out evenly, but it can make some types of searches a little trickier. And finally, geo-based, which is absolutely fantastic for speed because it puts the data physically closer to your users. So here's a good rule of thumb to remember. The crucial thing is picking the right tool for the job. If your number one goal is just handling crazy, unpredictable growth, then hash sharding is probably your best friend. But if you're all about making your app feel super snappy for users in, say, London and Tokyo, then geo-sharding is going to be your answer. Okay, awesome. We've sharded our data, so now we can scale. But, we've just created a brand new problem for ourselves. What happens if one of those machines, one of those shards, just dies? Poof, a whole chunk of our data is gone. The solution is simple in concept. Never, ever have just one copy of anything. And this, my friends, is called replication. The classic way to do this is a leader-follower setup. All the new data, the writes, go to one main server, the leader, which then copies it out to the followers. It's simple and it works, but you can get some lag. Then you have more complex setups like multi-leader or even leaderless systems. They give you way higher availability, but man, they open up a whole new can of worms. Like, what do you do when two people try to write different things at the exact same time? Okay, so remember that C for consistency from the CAP theorem? Let's circle back to that for a second. It turns out consistency isn't just a simple switch you flip on or off. Nope, it's actually a whole spectrum of choices. And you guessed it, each one comes with its own set of trade-offs. And this is such a perfect way to illustrate the point. Think about a banking app. When you transfer money, you need strong consistency. That balance has to be perfectly correct for everyone, right now, no exceptions. But what about something like a like count on social media? For that, eventual consistency is totally fine. Who cares if it takes a few seconds for the count to be the same in every country? The right model completely depends on what you're building. But here's the catch, and it's a big one. If you demand that strong consistency, you are almost always going to pay for it with speed. Or, a lack of it. To be 100% sure that every single node in the entire world has the latest data, the system has to pause, coordinate, and get everyone to agree. It's a direct, unavoidable trade-off: correctness versus speed.
Okay, we've laid the groundwork, we've covered the fundamentals. Now we're getting to the boss level. These are the really, really tricky problems that separate the good systems from the truly great, resilient ones.
And maybe the hardest problem of them all, the distributed transaction. Just think about placing an order online. The system needs to process your order, and it needs to take your payment, and it needs to update the inventory. But what if those are three totally separate systems, maybe even three separate databases? How do you possibly guarantee that either all three of those things happen, or if one fails, none of them happen?
Well, the old school answer was something called a two-phase commit. But honestly, it's often slow, super complex, and pretty fragile. So the modern, much preferred way of handling this, especially in the world of microservices, is a beautiful concept called the Saga pattern. So here's how it works. It's actually pretty clever. A Saga is just a series of small, local transactions. So step 1 updates its own little database and then kicks off step 2. Now here's the crucial part. If any step along the way fails, the Saga starts running compensating actions to undo everything that came before it. So, for example, if updating the inventory fails, it automatically triggers a refund for the payment. It's just a brilliant way to get that all-or-nothing consistency without a single, massive, brittle transaction. And building on that idea of handling failure, the best systems don't just react to problems, they anticipate them. Architects have this whole toolkit of patterns they use. You've got timeouts, which stop your system from waiting forever on a service that's just not responding. You have retries, which, well, they try again, but they do it smartly, with a bit of a delay. And then you have circuit breakers, which are awesome. They stop the system from just hammering a service that's clearly already down and struggling. I really want to pause on this point because it is so, so important. Just retrying a failed request sounds like common sense, right? But imagine thousands of users all retrying at the exact same time. You've just created what's called a thundering herd, and you can literally knock your own system offline. You can turn a tiny glitch into a catastrophic outage. This is why smart, controlled retries are absolutely essential.
Whew, okay, so we've been through a lot of theory, but let's bring it back to the real world. How are the biggest tech companies on the planet actually using all this stuff?
Well, what's fascinating is that they all made different choices based on those trade-offs we talked about. Look at Instagram. They shard like crazy, and they're totally cool with eventual consistency for things like like counts. Then you have Amazon's DynamoDB, which is all about availability, using a leaderless design. And then there's Google's Spanner, which somehow achieved the holy grail, global, strong consistency, by using things like atomic clocks. It just proves there's no single best way to do it. There's only the architecture that's right for your problem. So look, if you need to boil everything we just talked about down into one single nugget of gold, this is it. Think of this as your interview cheat sheet. This one sentence is a powerful summary of the entire philosophy behind building modern, scalable, resilient systems. So there you have it. We've gone from the absolute chaos of failure to a set of powerful principles for building consistent, resilient systems. And look, these aren't just abstract ideas for a whiteboard. These are the actual tools, the real blueprints for building the services that connect our entire world. So now that you know the architecture, what are you going to build with it?